from a purely qualitative perspective, the flux is a product of magnetic field and area. We integrate only in situations in which the magnetic field is not constant across the area. But in every other situation, we don't have to integrate. We generally know there's just some relationship for the magnetic field and the area. So in a basic term, it's this product. The area is getting smaller, so the flux is getting smaller. In order to try and maintain the state of the flux, if the area is getting smaller, then you're going to have to create a larger magnetic field to compensate for the reduction in area. So the direction of the current has to be to reinforce the magnetic field that's already there. So in this case, we'd have a magnetic field that's probably this way in this loop, because that would right-hand rule us a magnetic field that is also into the board to try and increase the magnetic field that's already there. That make sense? Now, what did I do wrong? I'm just sitting here. And when I say 3 ways, what I really want to impress upon you is that if you want to generate an EMF, this is how it's generally done. We can come up with ways that are different than this, but if you're trying to do it, this is what it is. There's moving a loop into or out of a magnetic field. Now, there's a corollary to this. You can also just move a magnet into and out of a loop. That would be the same thing, because that really is what number 2 is going to be about, which is you can change the magnetic field for a stationary loop. Now, if you're trying to produce electricity, well, one of these is easier than the other. But both of them would work. It's just that one of them is easier than another. And this is generally, if you're trying to produce some kind of usable electrical current, these are ways you could do it. I mean, how do you think we do it in this country right now? Well, turbine is a word. A turbine is one of these 2 or perhaps 3 things. And there's different ways to build turbines. Ultimately, in all cases in which we're talking a turbine, something is providing external work to cause something to spin. In almost every case, that's how we do it, because creating a motor that spins a drive shaft is something that we're very good at it, very aware of how to do it. So in every circumstance, regardless of what it is that we're combusting, burning, we're spinning something. So pick your favorite turbine. Even if we're not combusting something, if we're allowing water to flow over a dam, which we're doing less and less because most of the dams are empty, but if we're allowing water to flow over a dam, that's still causing something to turn. So if you're going to build something that is going to generate electricity, generate an EMF, and you know you're going to be turning something to do so, well, there's a couple of other options, right? You could have a single loop and put a permanent magnet somewhere in there that you spin around the inside of that loop. That would do it. That would generate an EMF. It's a constantly changing magnetic flux. And therefore, if you can just spin that magnet, you will be generating an EMF in the wire. Connect this out to all of your houses, good to go. And that's basically what they do. Now, we want to do this in the most efficient way possible. And we are still constrained by one side of this parameter. You get the maximum EMF if the rate of change of the flux is higher. It generates a larger voltage. But there's a whole lot of pieces missing here. Other things that aren't as obvious. Now, we're not going to talk all about generating electric power here, but I'm hopeful that you guys have a minor understanding about how most power stations work? Is that true? Do you have who can argue, who could say that they really have no idea? Okay, so there's a few of you have no idea. Well, that's too bad. It's really outside the scope of this course. You know me, I stick right to curriculum. But it gets its power from three different places, three different types of electrical generation, if we're not buying our power from outside the state. To the third way, which I did not talk about. We've talked about two of the basics, which is changing the magnetic field. That one's pretty easy. And moving a loop into and out of a magnetic field, that one's pretty easy. Those are very straightforward, and I think we have an idea about that. The last one's going to be a little bit more difficult for me to draw, so just give me a second, because this is the way that we actually do it a lot of the times. And in fact, later today, or maybe Monday, I'll break out a small generator. We'll generate a little bit of electricity. And don't get your hopes up, it's not that exciting. All right, so let's say that this blue loop is my loop of wire. Okay? And that I have it in such a way that the ends of the wire come out of this region where there's a magnetic field. And the magnetic field is pointed upwards currently. All right? Everybody can envision this? So these two are connected to my circuit, and I'm going to try and measure an EMF between them. Good so far? Regardless of the shape, we can probably imagine that there's an area here. Because I'm just going to call that area A. Is that okay with you guys? So the flux right now, based on what I've drawn, would just be B times A. Because I've lined them up. And we're looking at a uniform magnetic field passing through a region of space that has an area A. That all good? Everybody follow that conversation? What if, instead, I could take this loop and rotate it so that it looks a little bit like this? Why won't that one piece doesn't want to go away? Stupid piece. Bye. There we go. All right, so my loop of wire. Something like that. So I have a loop of wire that perhaps I can twist the loop inside the region that has a magnetic field. Now, careful here, the direction of the area will be that way, and it makes an angle of theta with the magnetic field. So now I have to add an addition to my calculation for flux, because the area doesn't line up with the magnetic field. Does that make sense so far? Everything good? Now, even now, under this circumstance, there's no EMF generated, because nothing's changing. But if I could spin this, even if it's at a constant velocity, then omega, which would be the rate at which I spin it, would be d theta dt, right? Be the rate of change of the angle. Well, what if, and I'm remembering things now, what if theta equals omega times t is my function for where theta is? I could write my flux as B times A times the cosine of omega t. Now my flux is changing, right? But at any instant, at any point in time, the inside of this is an angle measure, right? In fact, at t equals 0, the angle would be 0. You follow along? So omega would have to be measured in radians per second for this to be acceptable. You could put it in degrees per second, I guess, if you wanted, but, we know that we can convert angular values to different values. Now, the EMF produced would still have the same basic properties of what we've talked about. We'd have to look at the number of loops, and we'd have to look at the negative sign to indicate the direction of this current. But we can find the time rate of change of this function, can't we? You guys have a method for doing so? You'd have to take the derivative of the cosine function. I'm assuming at this point that you guys know how to do that. So the EMF, negative n, ddt of B times A times the cosine of omega t. Now, pretty straightforward. I think it's a pretty easy assessment to make. B and A are a constant, right? We're leaving them the same. So negative n B A. And we'll take the time rate of change of cosine omega t. So I know that this is going to cause a little bit of concern for Oliver, but I'm going to get a negative times a negative when I do this, so the negative disappears. But that negative was just there to do what? Yeah, Lenz's law. All right, took the derivative of cosine omega t with respect to t, produces negative sine, and omega, because I have to use the chain rule. Correct? You guys remember all of our calculus? This is old calculus, right? This is first semester calculus, I hope. Chain rule. All right. I'm going to collect the big parts, the parts that matter. And I'm going to set the sign over here out of the way. This is how most electrical power is produced in our country. We spin the wires. We have permanent magnets that are in place or electromagnets powered from something else, and we spin the wires, spin the coils, using some kind of brushless motor system that collects the EMF. Yeah, I knew I couldn't make it that far. But if you ask about the positive sign, I'm probably going to be frustrated.
You made that very clear. So, those two...
It's all the other crap I didn't make very clear. I'm just joking. Go ahead.
The little pokey parts on the bottom, would you have to attach those to something?
For this to be to create a true EMF, yeah, they would have to be connected to either side of my circuit.
How would you do that? Wouldn't it get tangled?
There are ways to do it. And if I have time, I had meant to go get this set up, but am I recording? But ultimately, here's the thing. Notice this EMF. It is directly related to how fast you spin the wires. That shouldn't be a surprise because that's the rate at which the area is changing relative to the direction of the magnetic field. I don't have to go through this with you, but do you understand that because this is a sine function, the direction of that current is constantly changing, and the size of that current is constantly changing. This produces an EMF that is a sine wave in function. So we get a true alternating EMF. This is how electricity is generally produced in most countries nowadays. We have, if you go to the walls here, our walls have a cycle rate of 60 cycles per second, which means the frequency of oscillation of the voltage is at 60 cycles per second. This represents the peak voltage that's produced. And if you guys have done any kind of work in mathematics, you understand that over one cycle, the net voltage is 0, because I have equal amounts of positive voltage and equal amounts of negative voltage. But you've probably learned that there are ways in which you can use that and find an average. Have you guys learned about things like RMS or anything like that? Okay. I didn't know how much has been gone over in your math class or not. People might wonder why we generate power like this, or why this is the method for us to generate power if it doesn't provide us with a constant current in one direction. First, there's a lot of reasons why there's benefits here. Some I can tell you about, some I can't. And one benefit of producing power this way is that using some simple relationships that we've already kind of talked about, you can easily step up or step down the voltage. It's not clear here, but do you understand that if you have an alternating voltage, you will also probably produce an alternating current? Does that make sense? Well, if you have an alternating current and you send that current into a solenoid, you understand you're going to create a alternating magnetic field. Does that make sense? Right? If the current is alternating, meaning it's getting bigger and smaller and going in two different directions, you'll generate a magnetic field that'll be going in two different directions. It'll go backwards and forwards. So you're going to generate a magnetic field this way. All you have to do is apply another set of coils near this one, and you could have the two coils interact. And the EMFs that are generated by one or generated by the other would be related to the ratio of the number of loops. I passed this around, remember? Did you notice that when you took it apart, there was one that had a very high loop density and one that had a very low loop density? Using a system like this, and we'll do this in class, you can step up or step down your voltage without losing any electricity or any energy. You're exchanging voltage for something else. And we'll be able to describe this, but these are called step-up transformers. It is very likely your car had one. A lot of them don't anymore, but older cars do. My car still does. It's a way of generating enough voltage to get sparks in the engine. You only have a 12-volt battery. That's not enough to generate sparks. But using a step-up transformer, you can ramp up the voltage so the spark plugs will fire. It's a simple way of changing voltage. We transmit power over power lines at very high voltages and very low current, so we don't lose very much in the resistance of the wires. Those power substations that you see where all the wires come down and there's a whole bunch of things that look like stuff out of science fiction, that's where the power is taken down from the high voltage power lines and dropped down to the 110 that goes to all of these outlets in here. What's even more amazing is that's not just what we do. In the U.S. power system, all of those outlets receive their power from a power box somewhere else that's getting 3 phases of electricity at once, all 110 volts. But the phases are all slightly out of phase from each other so that you can combine the signal and create 220 lines if you need it. Ways to get 220 volts out of 2 110-volt lines. So our power system's a little bit complicated, but there's other good reasons to use this kind of power besides the fact that it loses very little in transmission. Now, if you're concerned about, well, how do you use this? When we first did this, when we first electrified houses, do you know what the point of electrifying those houses was? It was 100% one thing: lights. We created electrical devices later, but until that point, there were no electrical devices. So why put electricity in homes? To stop them from burning down from oil fires. By having electrical lights that you could turn on and turn off, you created a convenience, but also a safety factor. And light bulbs light up no matter what direction the current's going in them. So using this kind of electrification was easy in getting lights. Nowadays, that won't be true. Most of your lights are LEDs, and they do care what direction the light is going, or the electricity is going. But it's really easy to take this and turn it into DC. Really easy. If you don't believe, how you measure the amount of energy is more complicated. And since most of our devices nowadays tend to need DC or some kind of off step of the 110 volts, we change this around all the time. I brought up RMS because RMS is a way of measuring the power delivered from something that is coming in a sine wave. It's called root mean square. What you do is to get an idea for how much useful energy there is, you square all the numbers first, which turns this into a signal that looks like that. And then you square root it. Root means square. So you take this, find the average, take the square root. And it basically works out to be about 0.707 of peak. Peak is what we have right here. So the peak voltage we get from the first part of this, and useful power, 0.707 if we use RMS. Having taken an electricity class, if you actually find usable energy, it ends up being about 67% of peak. But RMS is classically used in calculating the amount of useful energy from a AC source. So if you've never heard of RMS before, that's where it comes from. Now, that was a long way around the hill to say that there are two things you should probably commit to memory. Putting a loop of wire into a magnetic field generates an EMF while it goes in and an EMF while it comes out. It's worth memorizing it. Of the level of things to memorize, I'd put this at level 2, just below the things that are level 3, like electric field of an infinite sheet, infinite wire, stuff like that. This one's pretty good to have on hand. Knowing that the EMF is proportional to omega, really useful on multiple choice. Really useful on multiple choice. But ultimately, Faraday's law is pretty easy to use. And you've seen the 3 ways it shows up on the exam. For the last couple of weeks, I've been giving you guys magnetic field problems. And I've told you that I've only given you half the problems. Do you realize that every other part of the problem I've left out has always been how do you generate an EMF from that particular magnetic flux? Every one of them. The most notable is the one often, because I wanted you to have practice ahead of us actually doing it in class. That practice was to figure out how to calculate flux, which is why I purposely put it into our instruction before we did Faraday's Law. Do you remember these? These problems come in 2 different flavors, and you should remember both of them. In every case, there's either a constant current from the wire that's given to you here, and they take this and they move it away from the system, or the current has some kind of time variance. In both cases, they ask about the EMF that is produced inside this loop and the direction of the current. Go back to any one of those questions that we've had. That was the last part of the problem. Figuring out what the EMF is here. So at this point, you should be able to do those questions. And I think we should probably see all of them. The low-hanging fruit would be the one where this stays in place and you have a current like this. That was the one that was on the last FRQ you were sent home with. Do you remember? That was the exact same problem. They gave you the flux and then asked you to calculate the EMF. All you had to do was realize that the only part was taking the derivative of this with respect to time. Everything else was a constant. So if you have that homework question, you should do the last 2 parts of it. It's good practice and is pretty straightforward. I'd argue that the harder one is the one where this is pulled away at a velocity, say v. And you're asked to figure out the direction and the size of the EMF. Let's do the first part of that now since we have a few minutes. If this were the setup and I was to pull this away from the wire, can you tell me what the direction of the current would be? We're just talking about clockwise or counterclockwise. So again, we're not talking about this. We're talking about a constant current, and we're moving this away. You have to already know that the magnetic field here is out of the board. Right? As you move this rectangle away, is the magnetic field getting weaker or is it getting stronger? Weaker. So the flux, is it getting bigger or smaller? Smaller. So the current has to be in a direction to try and maintain the magnetic field that's there. It would have to be counterclockwise.